Okay, now it's time to talk about applications. Let's first look at the enharmonic oscillator. So we said that, okay, if you want to study the vibration of molecules, you can assume all the vibrations as harmonic. And of course, in the one dimension, we have the 1D harmonic oscillator. And the one-dimensional harmonic oscillator is governed by this potential, 1/2 m omega squared x squared, right? In which x is the displacement coordinate. But in reality, this harmonic potential is just a truncated potential, right? You truncate the higher order terms of the potential. What if the displacement is not that small? That means, what if the higher order terms are not entirely negligible? Suppose let's consider, well, two more terms, c times x cubic plus q times x to the fourth power, in which c and q are just two constant, okay? And they can be calculated from, for instance, the Morse potential. Right? They're just the coefficient in front of the third order term and the fourth order term, okay? So if we plot the potential function versus the displacement, what is the harmonic potential? Well, the harmonic potential is quadratic, right? This is the harmonic potential. This is quadratic. But in reality, you don't have a harmonic potential. In reality, you have higher order terms. This is what we really have, okay? Perhaps I should. So this is really an enharmonic potential, right? Because if the molecule is entirely harmonic, you cannot break a chemical bond, right? Because, well, essentially the potential goes to infinity, right? And you cannot break the chemical bond, right? But for enharmonic potential, yes, you can break the chemical bond, right? Because if you stretch the bound to a very, very large distance, then the molecule dissociates, right? That's actually closer to the reality. Okay. And of course, harmonic approximation is very good if you only consider the equilibrium geometry, or if you only consider tiny vibration around the equilibrium geometry. But what if we want to consider, say, a larger range? Okay? So we're not just considering the bottom point. We're not just considering the lowest energy point, okay? Which, of course, you can use harmonic oscillator approximation. What about we want to consider a slightly large vibration, Okay, so this is the vibrational anharmonicity. Vibrational anharmonicity. Now, for some molecule, actually, even if you're considering the vibration around the equilibrium geometry, because of the shape of the potential energy surface, the vibrational anharmonicity is very important. Okay, so in our example, let's just consider a little bit far away from the equilibrium point. Okay, and let's just consider, say, first and second order perturbation. Okay, so still the perturbative term, the x cubed term and x to the fourth power term are small. Okay, they are not large. The potential is still dominated by the harmonic term. Okay, so that's why you can use the perturbation. Okay. So what is our Hamiltonian? Well, the Hamiltonian is zeroth order Hamiltonian plus our perturbation, cx cubed plus qx to the fourth power. Okay, and c and q are small corrections. H0, the zeroth order Hamiltonian, of course, is our harmonic oscillator Hamiltonian, right? P squared over 2m plus 1 over 2m omega squared x squared, right? And using the definition of lowering and raising operator, we can rewrite it as h bar omega raising operator times lowering operator plus 1 over 2, right? Okay, here I just remind you the definition of raising and lowering operator. Essentially, the position can be defined as h bar over 2m omega square root raising plus lowering operator, okay? And the linear momentum can be defined as I m omega h bar over 2 times the raising minus lowering operator, okay? All right. So what is H prime? H prime is our perturbation, which is defined as Cx cubed plus Qx to the fourth power. All right. Okay. Now let's consider first order correction to the energy. Well, the first order correction is calculated by using the zero order wave function, H prime psi n zeroth order, right? What is psi n zero here? This is a zero order problem. At zero order, there's no perturbation, and therefore you have a harmonic oscillator, and therefore those are really the harmonic oscillator eigenfunctions, right? Harmonic oscillator eigenfunctions, right? And we know that the harmonic oscillator eigenfunctions are characterized by the quantum number n, by the vibrational quantum number n. So we can rewrite this as n h prime n, right? Well, here n is just the notation for psi n at zeroth order, okay? It's just a notation. All right. So n stands for the nth eigenket, or the nth eigenstate for the harmonic oscillator. All right. Now, our perturbation here has two terms. One term is x cubic, another term is x to the fourth power. Let's first look at n x cubic n. What is this? This is always equal to 0, right? Because our wave function at 0th order is either an even function or an odd function. And x cubic is always odd. So either you will have even function times an odd function, which is x cubic, times an even function. And this gives you an odd function, right? Or the harmonic eigenfunctions are odd, then you have odd times odd function times odd function, which gives you an odd function, right? So either way, you will have an odd function under the integral sign. And you are integrating over from negative infinity to positive infinity. And therefore, you will have exactly 0, right? So x cubic does not contribute to the first order correction. Okay? So suppose your oscillator only has one perturbation, that is say times x cubed. And then if you apply the first order correction, you will have exactly the same energy as a harmonic oscillator, okay? Because x cubic does not contribute to the first order correction, okay? But here we're considering cubic plus q times x to the 4th power. So we have another term in our perturbation, right? So we need to consider n x 4th n. This is, of course, not 0, right? Because this is not an odd function, right? And we know x to the 4th power can be written as the raising operator plus lowering operator to the 4th power, right? Look at this expression here. X is the summation of raising and lowering operator, and therefore x to the 4th power is proportional to the summation of the raising and the lowering operator to the 4th power. Okay. And of course, you can use the properties of the raising and the lowering operator to simplify this bracket, right? And some of the terms will be equal to 0, and some of them are not. What are the non-zero terms? We will have several non-zero terms. This is a non-zero term, which is equal to m plus 1, m plus 2. You just use the property of raising and the lowering operator. Okay, this is another non-zero term, and this is equal to n times m minus 1. This is equal to m plus 1 squared. This is equal to n squared. This is equal to n times m plus 1. And the last non-zero term is this is also equal to n times m plus 1. All right. So those are all the non-zero terms, right? You see here you have x to the 4th power, then you will need to expand a plus plus a minus to the 4th power, and you have many terms. But a lot of those terms are equal to 0. And these are the only non-zero terms. Okay? And therefore, if you consider the perturbation caused by qx to the fourth power, you simply add all those non-zero terms together, and you have q times h bar over 2m omega squared times 6 n squared plus n plus 1 over 2. All right? So this is the first order correction due to the x to the fourth power perturbation. Now, it's ready to write down the energy. What is the energy of the operator? Well, the energy of the operator is the zeroth order, which is just the energy for a harmonic oscillator, which is m plus 1 over 2 h bar omega, plus the first order correction. And we know that x cubic does not contribute to the first order correction. And therefore, the only correction we have comes from x to the fourth power, which is equal to 3q h bar squared over 2m squared omega squared n squared plus m plus 1 over 2. Right? So this is the energy level of an n-harmonic oscillator with two perturbation terms. One is x to the cubic, another is x to the fourth power. This energy is correct to the second order. So what's the difference between a harmonic oscillator and an n-harmonic oscillator? As you can see here from the energy level expression, an harmonic oscillator does not have equally spaced energy levels. Right? What does that mean? That means if you look at the harmonic oscillator, okay, this is harmonic. Which is quadratic. Well, the lowest energy level is, of course, the 0 point level, which is not equal to 0. And the next is if you look at the difference between the level n and level n minus 1, they are equally spaced, right, for a harmonic oscillator, right? But for an harmonic oscillator, that is for a real molecule, a real vibration, if you increase n, En minus En minus 1 is decreased. Right? So yes, still you have a 0 point energy level, and then the space between different energy levels becomes smaller and smaller. Right? Okay. If you look at En minus 1, right? You will see that when you increase the quantum number, the distance between the neighboring energy levels becomes smaller and smaller. You will have a very dense spectrum. Okay, this is an harmonic oscillator. Now, let's look at the second application. Molar-Plast perturbation theory. This is really about how to find out a more reliable energy level for a molecule, for a multi-electron system. Now, previously, we talked about Hartree-Fock theory. And we can say that Hartree-Fock theory is correct to the first order. Why is that? Well, what is our zeroth order Hamiltonian? Well, in Hartree-Fock theory, this is just the summation of the Fock operator for all the electrons, right? This is the Hamiltonian for the Hartree-Fock theory. Again, the Fock operator, and just remind you what is the Fock operator. Fock operator is the kinetic energy of electron I plus an effective potential. The Coulomb operator minus the exchange operator, right? So this part is really the effective Hartree-Fock potential. So the electron, essentially, one electron is moving under an averaged potential, and this potential is the Hartree-Fock potential, right? And of course, the Fock operator, is a single electron operator, because for electron I, the Fock operator only depends on I. But of course, implicitly, the Coulomb operator and the exchange operator depends on the motion of other electrons. So this is actually an averaged effective potential. So what is the zeroth order question? What is the zeroth order eigenvalue problem? Well, the zeroth order eigenvalue problem is really right. Now I just put a parenthesis here, right? What you have is phi I is just a spin orbital, right? Epsilon I is just the Hartree-Fock orbital energy. Right? It's just the Hartree-Fock orbital energy is actually the zeroth order approximation. If you take the summation of the Fock operator as your zeroth order Hamiltonian, right? And what is the Hartree-Fock wave function? Well, the Hartree-Fock wave function, in this case, we're considering it as a zeroth order wave function. This is a Slater determinant, right? Phi 1, 0, phi a, 0, until phi n, 0, right? This is the zeroth order wave function, right? Which is really a determinant, right? Okay. So you wonder, okay, if you think Hartree-Fock theory as the zeroth order, and I know how to solve the Hartree-Fock equation, okay, because we have this Rosen equation. You can use the SCF, the self-consistent field procedure, to calculate the zeroth order Hartree-Fock wave function. Then what is our perturbation? Well, if we view the difference between the exact electron-electron interaction and the effective Hartree-Fock potential as your perturbation. Now, let me be more clear here. Now, the first term is the term that you should have in an exact quantum mechanical problem, right? Because quantum mechanically, all the electrons are interacting with each other. So this term, 1 over Rij, is the exact electron-electron interaction. right? This is the exact electron-electron interactions. And what is summation V Hartree-Fock I? This is the effective interacting potential. In Hartree-Fock theory. Right? In Hartree-Fock theory, okay, you assume that all the electrons are actually moving independently. It's just for a single electron, this electron is moving under an averaged potential. This averaged potential is generated by all the other electrons. But still, you do not have the explicit electron-electron interaction term in the Hartree-Fock equation, right? Instead of considering this electron-electron Rij term in your Hartree-Fock equation, you used an averaged effective single particle potential, right? This is the difference between the exact situation and your approximated Hartree-Fock theory. Okay, so if you treat this difference as your perturbation, let's see what we will have. What is the zeroth order? The zeroth order energy is just the zeroth order wave function, zeroth order Hamiltonian, and the zeroth order wave function, right? This is just the expectation value. And this is equal to sigma I, epsilon I, 0, right? Well, because H0, which is the summation of the Fock operator, is a one electron operator, right? And according to the Slater-Condon principle, or Slater-Condon rule, we have the summation of the one electron energy, right? Epsilon I is the one electron energy, or the Hartree-Fock orbital energy. What is E1? E1 is the first order correction to the energy, which is psi 0, the perturbation, and psi 0, right? And H prime, of course, is sigma Iij. This is the exact two electron interaction, psi 0, minus psi 0 summation of the Hartree-Fock effective potential, psi 0, right? And if you remember our Slater-Condon rule, you can write down this as 1/2 summation AB are the molecular orbitals, right? JAB minus KAB times delta MS1, MS2, right? This is the Coulomb repulsion minus the exchange repulsion if electron 1 and electron 2 are in parallel spin. Okay, minus sigma A, phi A 0, V Hartree-Fock, phi A 0, right? And this is 1/2 sigma AB, JAB minus KAB, delta minus summation AB, JAB minus KAB delta, right? And this is just equal to negative 1/2 summation AB, JAB minus KAB delta, right? Okay, this is just essentially a review of the Hartree-Fock potential, right? Remember, the Hartree-Fock potential is defined by using the exchange operator and the Coulomb operator, right? So when you evaluate this expectation value, essentially what you really have is, here I just put a remark to remind you what we are having here. So essentially what you're doing here is just phi A, I, the Coulomb operator, JBI, phi AI, right? And this gives you JAB, the repulsion between the electrons on orbital A and orbital B, right? Another part of the Hartree-Fock potential is phi AI, KBI, phi AI, right? This gives you the exchange interaction between two electrons, right? Okay. And therefore, what is the final energy? The final energy is just equal to the zeroth order plus the first order, right? If we look at the first order correction, then this is the summation of the Hartree-Fock orbital energy minus 1/2 sigma AB JAB minus KAB delta MS1 MS2, right? So this is exactly the Hartree-Fock energy, right? E is the Hartree-Fock energy, right? That is to say, the first order perturbation well, since we're doing a multi-electron system for real molecules, this kind of perturbation theory is actually called the Moeller-Plast perturbation theory. Right? This is called MP1, which is an abbreviation for Moeller-Plast first order perturbation, is equivalent to the Hartree-Fock theory. Right? In other words, the Hartree-Fock theory is correct to the first order. So what is our perturbation? The perturbation is the difference between the exact two-electron interaction and the Hartree-Fock effective potential, right? This is the perturbation. And then you do the perturbation treatment, which is also called the Moeller-Plast perturbation treatment. You can show that the Hartree-Fock theory is actually correct to the first order. The first order approximation of the energy for this multi-electron system is exactly equal to the Hartree-Fock energy. All right. And that's why for lots of main group molecules at their equilibrium geometries, Hartree-Fock theory works just fine qualitatively, especially for dipole moments or charge distribution, or for analyzing the contribution of atomic orbitals to a chemical bond. So Hartree-Fock theory actually provides a very good zeroth order or first order approximation. Okay. Now, what is the second order? The second order is called MP2. Right? We still have the same H0 and the same H prime, right? We have the same perturbation. If we do the second order Moeller-Plast theory, the second order Moeller-Plast perturbation theory, then we have the energy is equal to the zeroth order plus the first order plus the second order, right? Well, we already showed that the zeroth order plus first order correction is just equal to the Hartree-Fock energy, right? Hartree-Fock is correct to the first order. Plus, what is the second order energy correction? Well, the second order energy correction is sigma n is not equal to 0. 0 is the ground state, okay? 0 h prime n squared over E0 at the zeroth order minus En at the zeroth order, right? At the zeroth order, this is just the Hartree-Fock energy, right? So here, this 0 means the ground state zeroth order wave function, which is the ground state Hartree-Fock Slater determinant, right? E0 again is the ground state Hartree-Fock energy. What is n? N is not the ground state. You see here in the summation, n is not equal to 0. That means n is not the ground state. So this is the excited state, right? This is the excited state, zeroth order wave function. N is the excited state, zeroth order wave function, which is the excited state Hartree-Fock wave function. Okay, so the electrons are not at the ground state. Okay, you redistribute the electrons to higher energy levels as solved by the Hartree-Fock theory. And En0 are the corresponding excited state zeroth order energy, right? So most importantly, this tells us actually MP2, the second order perturbation theory, effectively introduce double excitations via the second order term, which is 0 h prime n, right? Why it's the second order? Well, why did I say that it introduced double excitations? Well, first of all, based on Brown theorem, right? Based on Brown theorem, the singly excited determinants do not interact with the ground state Hartree-Fock wave function, right? Do not interact with the ground state Hartree-Fock wave function, which is denoted as 0 cat or 0 bra here. So of course, you will not have single excitations, right? Because it does not contribute to this bracket. It does not contribute to the second order perturbation. And we know from the Slater-Condon rule that because H prime, which is our perturbation, is a two-particle, this is a two-particle operator. And based on Slater-Condon rule, we know that if n differ from 0 by more than 2 spin orbitals, then this integral is equal to 0, right? Then n does not interact with the ground state Hartree-Fock wave function, right? This is from the Slater-Condon rule. And therefore, you will not have higher excitations. You will not have triplet or quadruplet, right? Because here, for the second order perturbation theory, really what we're looking at is this integral. So you introduce double excitations, okay? Now, let's give you some specific examples about the performance of Hartree-Fock theory versus MP2, the second order Moeller-Plast perturbation theory. For instance, if you consider the singlet-triplet gap, for this molecule, the nitrogen protonated to 5-pyridine, okay? If you consider the singlet-triplet gap. Hartree-Fock theory gives you the gap is equal to 87.4 kilocalorie per mole. And MP2 tells you actually the gap is negative 4.1 kilocalorie per mole. Okay? And the experiment value for the gap is actually negative 5.0 kilocalorie per mole. So you have a significant improvement for the answer, right? The first step is to solve the Hartree-Fock equation. The second step is to apply the second order perturbation on your zeroth order energy, right? And then you get negative 4.1 as the singlet-triplet gap. Of course, you need to do this calculation for the singlet state and for the triplet state. And then you do the difference between the singlet energy and the triplet energy. Okay. How about reaction barrier height? Right? If you think about the arrow in kilocalorie per mole, what is the error of the method? Okay. Well, reaction barriers are very important. We can select a data set which include representative reactions. Okay. For this set of the representative reactions, we know the exact reaction barriers. And then we solve the Hartree-Fock equation. And we do the MP2 for this set of reactions. Let's see what is the error given by the Hartree-Fock equation. Typically, the error for predicting the reaction barriers for Hartree-Fock is about 10 kilocalorie per mole. But for MP2, it's only about 5 or less than 5 kilocalorie per mole. So you see, this is also a very important, a very significant improvement over the Hartree-Fock energies, right? MP2 is actually a very good choice. The second order perturbation theory based on the Hartree-Fock zeroth order wave function is a very good choice for recovering the dynamical correlation. If, here's a catch, if the Hartree-Fock wave function, which is the zeroth order wave function, is qualitatively a good description for your system. For instance, for the main group molecules around the equilibrium geometry, the Hartree-Fock wave function is qualitatively fine. But if you consider the dissociation limit and when you consider the two fragments together, not separately, then Hartree-Fock wave function is bad, right? Especially if you do the restricted Hartree-Fock, then it's really bad, right? Then in this case, even if you do MP2, it will not help you a lot, okay? So if the Hartree-Fock wave function for your system is qualitatively good, then you do MP2, you can get a very good energy, okay? All right, This is our second application. The last application we will see in this course is the first order spin-orbit coupling. Of atoms. So in a central field, the potential only depends on the distance between the electron and the origin, right? That's the central potential. That's the central field. And the commutator between the angular momentum and the total Hamiltonian is equal to IH bar R cross the negative gradient V. This is easily derivable. And you see, since the negative gradient V is really the force, right? But for a central field, for an electron in a central field, this force is a radial force, right? That means this force is always in the direction of the position vector, right? And therefore, essentially, you will have a position vector cross another vector that is along the position vector. And of course, this cross product is equal to 0, right? If you consider the spin operator, NH, and this is also equal to 0. That means the total angular momentum and the total spin are conserved, right? Why is that? Because based on the equation of motion, dA, expectation value dt, is equal to is equal to 1 over IH bar, expectation value AH, right? Of course, here, the operator itself does not depend on time. So if this term, this commutator is equal to 0, then the expectation value of this quantity does not depend on time. That means the expectation value of A is conserved, right? So in this case, the total angular momentum and the spin are conserved. And that's why we can use L and S as good quantum number. Right? That's why we can label a particular state by using L and label a particular spin state by S. They're all quantum numbers, right? That's because L and S, the angular momentum and spin, are really conserved. And that's why you can use the corresponding quantum number, small l and small s, as the labels for the quantum state. Now, let's consider a specific case, the so-called spin-orbit coupling. Suppose you have an electron that's moving around a center, and this will generate a magnetic field, right? Because you have a changing current. So this will generate a magnetic field, BL. This magnetic field is generated due to the motion, due to the orbital motion of the electron. And the magnetic field is actually proportional to R cross V. V is the linear velocity of the electron, right? In the classical electromagnetism, this is called Biot-Savart law. Right? Okay. And, well, because electron is spinning, right? The electron spin can give you a magnetic moment, mu s. It's also a vector, right? This mu s is proportional to the spin of the electron, right? This is the magnetic moment. To be more specific, This is the spin magnetic moment, right? So essentially, when you see this, what you're doing now is essentially you put a small magnet in an external magnetic field. Of course, this magnet will interact with your external magnetic field, right? So you will have interaction between BL and mu s. Now, this magnetic field is really generated by the orbital motion of the electron. You're not adding another magnetic field, right? This magnetic field is purely generated by the orbital motion, right? So I should say, technically, it's not the external. This is the intrinsic magnetic field, right? All right. And this interaction will give you the coupling between orbital motion, which is characterized by the angular momentum, and spin, which is characterized by the spin, s. What is the interaction? Well, we know that the interaction is actually negative b times mu, right? So this interaction, this energy is called spin orbital coupling. This interaction is called spin orbital coupling, right? So the spin orbital coupling operator, or the energy operator, is proportional to L dot S, right? So if you look at, this is your B, this is your mu. So if you do a dot product between B and mu, essentially you will have a dot product between the angular momentum and S, right? And alpha, of course, is just the coefficient in front of this L dot S. And this coefficient, it turns out, is actually proportional to the nuclear charge to the fourth power. And therefore, if you have a very heavy atom, this spin orbital coupling can become very, very important. You cannot ignore it, right? Previously, when we talk about, okay, we just talk about H, right? We talk about H here. We're not considering the spin orbital coupling. The H here is just the kinetic energy of the electron plus the central potential. That's it. But actually, if you consider this interaction, this tiny interaction, for some elements it's tiny, but for some elements it's actually quite important. This interaction between the spin and orbital angular momentum, then your H becomes H0 plus the spin orbital coupling. H0 is just your regular Hamiltonian, which is just the kinetic energy plus the central potential. Okay? But when you consider this, now it's easy to show that L dot S, this commutator, is equal to negative IH bar L cross S. This is not equal to 0. Similarly, S L dot S is equal to negative IH bar S cross L, which is equal to positive IH bar L cross S, is not equal to 0. Okay? And therefore, because of this term, because of this spin orbital coupling, the angular momentum no longer commute with H. The spin no longer commute with H. Of course, LS, these two operators, they always commute with each other, right? Because, well, L is the external motion, the S is the intrinsic motion of the electron. They always commute with each other. However, because of the consideration of the spin orbital coupling, L no longer commute with H. S no longer commute with H. That means the total angular momentum and total spin are not conserved when the spin-orbit coupling is included. That is to say, L and S are no longer good quantum numbers. Especially for heavy atom, when you consider spin-orbit coupling, you can no longer just use L or S to describe the state of your system because they are not good quantum numbers. At the zeroth order, they are. Okay, if you just look at the zeroth order H, yes, you can have L and S as your quantum number. But if you really consider the exact H, which include the spin-orbit coupling term, you can no longer use small l and small s to denote the quantum state of your system. Instead, you have to consider the total angular momentum. Which is J is equal to L plus S. This is the total angular momentum. You should do a vector summation for the orbital angular momentum and the spin angular momentum. Why is that? Because if you do J L dot S, this is equal to L dot S plus S L dot S. This is equal to 0. Okay? Because L dot S is negative IH bar, L cross S. LS is equal to positive IH bar, L cross S. So if you sum them together, this commutator is equal to 0. Right? In other words, the total angular momentum commute with your exact Hamiltonian. So J, the total angular momentum is conserved when you consider the spin-orbit coupling. And therefore, the quantum number you should use are the total angular momentum quantum number and the projection of the total angular momentum. Okay? That's why when you write down the atomic term symbol, you write down L to S plus 1 and J, right? If you only look at the spin and the orbital angular momentum, they're okay. They're a good quantum number at their order. But if you consider the spin-orbital coupling, you have to use the J quantum number, which is the quantum number for the total angular momentum to label your quantum state. Okay? And of course, how to get the total angular momentum? Well, in terms of the quantum state, at the zeroth order, you can have L1, M1, L2, M2, right? L1 and M1 are the quantum number for the first electron. L2 and M2 are the quantum number for the second electron. L is the angular momentum quantum number. M is the projected quantum number, the projected angular momentum quantum number, right? And this is one state. And for the spin, you can have S1, MS1 for the first electron, S2, MS2 for the second electron. And then you can use the addition of angular momenta that we talked about in lecture 10. And actually you have practiced on problem set 3. You can construct Lm, that is the total angular momentum and the projection of the total angular momentum, right? And you can add the angular momentum for two particles together. to get S and ms, right? This is the total spin and the projection of the total spin. And then you can combine this to J, mj, right? This is the so-called LS coupling scheme, right? You're first, essentially what you're doing now, you're trying to, okay, I'm adding the angular momentum together, the orbital angular momentum together to get the total orbital angular momentum. And I'm adding the spin together to get the total spin angular momentum. And then you do the total angular momentum is equal to L plus S, right? That's the so-called LS coupling. There's another way to do the coupling. You have, at the zeroth order, you have L1, M1, S1, MS1. You just look at the first electron, okay? You have the angular momentum quantum number for the first electron, the projected angular momentum quantum number for the first electron, the spin for the first electron, and the projected spin for the first electron. And then you can construct the total angular momentum for the first electron and the projection of the total angular momentum for the first electron, right? Similarly, you can do this for the second electron. Then you can construct J2, MJ2, right? And then you can combine these two to get the total angular momentum and the projection of the total angular momentum. This is called the JJ coupling scheme. Okay? Essentially, what we're doing now is you do L1 plus S1 is equal to the total angular momentum for the first electron. You do L2 plus S2 is equal to the total angular momentum of the second electron. And then the total angular momentum is equal to the total angular momentum of the first electron plus the total angular momentum of the second electron. This is the so-called JJ coupling. LS coupling and JJ coupling will actually not give you the same answer in terms of the energy or in terms of the coupled quantum state. But as a general rule, actually, LS coupling is fine for most heavy atoms. This is fine for most heavy atoms. And for some of the heavy atoms, you have to consider JJ coupling. For instance, lanthanum, right? For instance, if you consider lanthanum, then you need to consider JJ coupling. All right. Now let's talk about the energy. What is the energy? Because here in this course, we're only talking about the first order spin-orbit coupling. So let's just consider the zeroth order plus the first order, which is the zeroth order plus what is the first order? Well, the first order is the wave function, zeroth order wave function. You can or you can couple the L and S together to give you capital J and the projection mj. What is our perturbation? Our perturbation is L is alpha times L dot S, Jmj, right? So here, this term is the spin orbital free energy. And this term here is denoted as energy spin orbit coupling for the J quantum number. So this is the spin orbit coupling energy. Spin orbit coupling energy. Right? Because it depends on the actual quantum number J you are considering. So that's why I write parentheses J here. Okay. Now we have a little bit algebra because here we have a product of LS. In order to evaluate this, we can essentially write L dot S as 1/2 the total angular momentum squared minus L squared minus S squared, right? L squared is just L dot L The s squared is just s dot s. And this is equal to 1 over 2 j squared minus l squared minus s squared, right? L dot L is just the magnitude of L squared, and I just read it as L squared, okay? And of course, all of those are operators. So what is J, Mj? What is our first order correction? L dot S, J, Mj. This is equal to, well, you see, you just plug in this back into the first order correction. So you will have alpha over 2, you will get J plus 1. Right here, now this J is the quantum number. Minus L plus 1. Minus S plus 1. Okay? Here, J, L, S are quantum numbers. Here, J, L, S are operators. Okay? So essentially what you have is you have the bracket JMJ, J squared operator, JMJ. And of course, this is JJ plus 1. Well, this is in atomic unit. If you're using standard unit, then this is JJ plus 1 H bar squared, right? This is the basic properties for the angular momentum because JMJ is the eigenfunction of J squared. Similarly, if you put L squared here, you will have L plus 1. If you put S here, you will have S plus 1. This is the zeroth order function. At the zeroth order approximation, JMJ are the eigenfunctions of J operator, L operator, and S operator. So finally, the spin orbital energy for quantum number J is actually, if you do SOJ minus SOJ minus 1, you will get alpha times J. This is a very important result. So here, this part is the spin orbital correction, right? This is the first order correction. And ESO is just, if you think about E0 plus the first order correction. The first order correction is given by this result, right? And if you consider the difference between two energies, E0 are canceled out. So essentially, it's just the difference between the first order correction. And this is proportional to J. This result is experimentally observable. And this is actually called the Lundy interval. Experimentally, if you observe the atomic spectrum, let me just give you a simple example. Atomic spectrum for, say, titanium, right? Its electronic configuration is 3d2, 4s2, okay? So if you do not consider spin orbit coupling, so this is the energy level. This is E0, right? This is the spin orbit free ground state, right? If you use a term symbol, then you can write this as 3F. F is the total angular momentum. 3 is the spin multiplicity, which is equal to 2s plus 1. In this case, S is equal to 1 because you have two long electrons, right? So on the d orbital, you have two unpaired electrons. and they're all spin up. And therefore, S is equal to 1, and 2S plus 1 is equal to 3. And here we have a 3 here, right? And what is the total angular momentum? Well, that's F, right? 0 is denoted as S, 1 is denoted as P, 2 is denoted as S, P, D, F, right? So the total angular momentum is equal to 3. That's for F, right? The notation is F. Why? Okay. Why is 3? Because this is positive 2. This is positive 1. This is 0. This is negative 1. This is negative 2. And therefore, you have positive 2 plus positive 1. And therefore, the total angular momentum is positive 3. Okay. You can do this because you are not considering the spin-orbit coupling. So you can use L and S as quantum numbers. And now, if you consider spin-orbit coupling, the energy level will split to 3 energy levels. Okay, this one is called 3F2. The total angular momentum is, the total angular quantum number is equal to 2. This is 3F3. This is 3F4. All right, 4, 3, 2 are J, the quantum number. And experimentally, if you measure the energy difference between different levels, you will have 217 wave number and 170 wave number. This is the experimental atomic spectrum. You measure the lines, okay? And of course, this state, this lowest energy state, is actually the true ground state, right? So this is the so-called spin orbit included ground state. So you do see the energy difference here, right? This energy difference between the spin-free ground state and the spin orbit included ground state is actually the correction you have to apply if you really want to calculate the energy more accurately. Okay, but this is not the important point here. The important point here is experimentally you indeed observe the Lange interval rule, which means if you consider J is equal to 4 minus J is equal to 3 over J is equal to 3 minus J is equal to 2. According to our derivation here, this should be proportional to J, and in this case, should be 4 over 3, right? You see, here this is J is equal to 4. Here, this is J minus 1, right? This is 4 minus 1. This is J is equal to 3, and this is 3 minus 1. So it should be proportional to 4 over 3, right? According to our rule. Right? And based on the experiment, we know that 4 over 3 is basically 217 over 170. Right? So experimentally, indeed, you validated what we just derived. This is Lange interval rule. And this is all derivable from the first order perturbation theory. The spin-orbit coupling is actually general. Here we talk about atoms, but actually it's general in molecules, radicals, solids. Whenever we have a very heavy atom, for instance, a transition metal atom, the rule of spin-orbit coupling cannot be ignored in many cases.